All right, so the last two stories I want to touch on are with exoplanets because it has been a big month for exoplanet news. Europe's had a couple of exciting successes. One of them is that they've just gotten the green light for their next exoplanet satellite, which is very excitingly named Characterizing Exoplanets Satellite. Wait till I get to the name of some of these exoplanets, you'll be thrilled. So that's exciting. We also, in March, celebrated the 10th anniversary of the launch of the Kepler Space Telescope, which really revolutionized how we study exoplanets. And at the same time, we also were able to finally confirm the very first exoplanet candidate that Kepler, ever found. So we thought this was a false positive. It saw a dip of light of what we thought was a Neptune-sized planet. And then they saw a second dip from when the planet passed behind the star. And we thought, that can't be right with a Neptune-sized planet. But new study just came out. We've got what they call a hot Jupiter orbiting a approximately sun-sized star. That is pretty exciting to actually get confirmation of that. But overall, it's been an exciting month for these crazy hot Jupiter planets because we've also been able to do some work here on Earth to better understand them. Okay, so first things first, what is a hot Jupiter? Well, it's certainly not something we have here in our solar system by any means. So hot Jupiters are these planets that are gas giants like Jupiter that are anywhere from about half the size of Jupiter to 11 times as massive as Jupiter. But they orbit very, very close to their parent star. So they have orbits that are an order of 10 days or less. Pretty crazy. The one that Kepler was just confirmed has an orbit of 3.8 Earth days. So it's whipping around. The good news about this is it means that these types of planets are really easy to detect. If we're using the transit method, which is what Kepler used, which we're basically looking at the light from the star and it's going along, and then something goes in front of it, and that light dips. And then it comes back. We need at least one more dip to confirm that this wasn't, say, a big star spot, much like sunspots, or some other sort of anomaly. And with a short period of a few days, we can look for second, third, fourth, fifth eclipses, no problem. Easy amount of data gathering time. And these dips in the light are going to be pretty big because these planets are large and they're close to their stars, so they're going to block more light. But we can also use other methods to discover these planets. There's a method called radial velocity. And what that is looking at the light from the star and how it wobbles. So we think of the sun as holding all of the planets in orbit and tugging on Earth, for instance. But Earth is exerting a little tug on the sun as well. And when you have something like a hot Jupiter, it's going to exert a bigger tug. So we can look at the light, the fingerprint of the light, called the spectra. Ugh, I'm going to get my words here tonight. The spectra, and we can see how when it moves towards us, it shifts to the blue, and then when it moves away from us, it shifts towards the red. So these hot Jupiters, we can find multiple ways. So we know of a lot of them. Here are a few artist conceptions of some of the ones that we found. But we want to know more about them because, again, we don't have this here in our own solar system. So we know these temperatures are brutal, anywhere from 1,000 to 5,000 degrees Fahrenheit at the surface of these planets. But what is the atmosphere like? And we can tell a little bit from spectroscopy. But we were able to create this in the lab here at NASA, and they followed a pretty simple recipe. They listed this recipe like a recipe you'd be going to bake brownies for, which is super fun. So they say start with a beaker of hydrogen, add in a dash of carbon dioxide, I believe. I have to look at our recipe here real quick. And then you want to bake this at about 2,000 degrees for 200 hours and bathe it in UV light. All the press releases are very careful to say, please don't try and eat this alien atmosphere. You've been warned. And so they were able to look at these. So here's a great example of another hot Jupiter. Carbon monoxide, excuse me. And so they tried taking mostly hydrogen, a little bit of carbon monoxide, and just baking it. But they didn't see one key property that we see in these hot Jupiters, is that they're really hazy on the outside edges. And this is weird because there shouldn't be enough pressure to form clouds on the outer edges of these planets. And so they then bathed it in that ultraviolet radiation, and they were able to create aerosols, so basically solids suspended in a gas. Think a kind of layer of fog or a brown cloud over Denver, right? We see these in these hot Jupiters, which had really been boggling our minds. But they were able to reproduce this, and this was the first time we have evidence that radiation plays a key role in the development of atmospheres of planets, at least these hot Jupiters. So that was really exciting. And so we're excited to continue to learn about these, and maybe we can do further experiments here in labs about other types of atmospheres around exoplanets, as well as doing those telescopic observations. So I thought that was just a little different. The other one just came out today. There was a press release because there was a publication in Astronomy and Astrophysics of Europe's other big success. They've been able to use their Very Large Telescope Interferometer. Again, creative with the naming, guys. We get large and very large. And they were able to directly image an exoplanet. And I have to look at the name, I apologize. HR 8799e. Yay! And so this is about 129 light years away. It's located in the constellation Pegasus. It's one of several planets in this exosystem, but this is another big Jupiter-like planet. But we're really excited because we've been able to see it in more detail than we've ever been able to see. Directly imaging an exoplanet, not getting hints that it's there from other avenues, but actually getting a photograph of it. This is not the photograph. This is an artist's conception. Fun story. They didn't publish the photograph, but that's okay. Still exciting. So what is this interferometry? Why is this so key? So this is a tool very familiar to radio astronomers. You can think of the Very Large Array. You might have seen pictures of that in New Mexico, or if you've watched Contact, the movie that plays a big role, or the Very Large Baseline Array, again, creative names, and hopefully the Square Kilometer Array. But this is using visible light. And so what they do is they combine light, in this case from 4 different telescopes, and that gives us a better resolution than just one telescope alone. So when we build telescopes, the bigger they are, the bigger light gathering capability they have, but they also give us better resolution, so we can see smaller and smaller things on the sky. When we do interferometry and combine light from multiple telescopes, we don't get all the advantages of having one telescope that's, say, a mile across, but we certainly save a lot of money, and we do get that better resolution. So this is down in Chile. This is their European Southern Observatory's telescope. Each of these are an 8.2 meter telescope, so they're big to start off with, and just really impressive. And what they were able to do is then really look at the spectra of the atmosphere and separate that out. So this is the image from Keck, because this has been imaged before. This is our little planet there. The new images that came out are about 10 times higher resolution than this. And that gave us some really startling results about the atmosphere. So we'll go back to this picture here. So we already knew it was a super Jupiter, meaning it's bigger than Jupiter, but it's a gas giant. But the reason we keep going after this specific planet with an uncreative name is that it's an example of something we don't have here on Earth. It's a planet that's only 30 million years old. Most of our planets are about 4 billion years old. So this gives us a really interesting insight into the planet formation, the formation of planetary systems in and of itself. And this planet is literally still glowing with the light and heat of its formation. So it's about 1800 degrees Fahrenheit, but it's radiating out light from the center. And what surprised astronomers is that atmosphere didn't have as much methane as we expected. It had a lot more carbon dioxide than we thought, which means there's got to be some sort of really turbulent, big vertical wind that's pushing things around, that's not allowing that carbon dioxide to mesh with the hydrogen there and form methane, which we see and expected to see in a lot of young planets. But they also found some really interesting clouds of silicates and iron. Iron, yes, that's not something you normally think of. I like whoever reacted there, thank you. And so they think is happening is there's this whole planet has to be enveloped in basically a gigantic storm. That there is convection, so think boiling a pot of spaghetti or not having an air-conditioned house in summer, right? Heat rises, cool air sinks, or material in general. So you've got all this heat source here, that's heat from the formation of the planet, that is moving heat around. It's causing that iron and those silicates in the clouds to break apart into their component pieces and rain back down towards the center. And it's just this planet that's going through massive amounts of physical and chemical change. And it's just so, again, so different from anything we've seen in our solar system. And really opening our eyes to the variety of planets and planet dynamics that we might find out in the universe. So I'm hoping that image will eventually be released. But this press release came out about 3 hours before we started here. So we'll see, hopefully, so stay tuned.